Okay, so I'm going to do again those examples on the Heisler chart so that you guys have it. You can pause it, rewind it, etc., and see exactly what to do in case you're still having problems reading those charts. So this first example is for a plate. The given information is right here. K is 25, alpha was 6.99 times 10 to the minus 6, and that was something that you would have found in the data tables. I wanted to make sure that you were really very aware of the fact that when you read those in the data tables and in the appendix of your book, what it says is at the heading, look at it real closely, it says alpha times 10 to the 6th equals, and then you read some number like 1.5. So that means if you just use this at like an algebraic equation, alpha is that 1.5 or whatever number times 10 to the minus 6th. Okay, so that's going to be really important when you're reading those tables, or you're going to get some strange answers that make no sense. Now the other thing is they talk about the thickness. So the thickness is 0.03 meters or 3 centimeters, and thickness is this, distance from the lower edge to the top edge of our little plate. The way this is done is the center is measured at the center line as 0, and x counts from the center to the edge, so either above or below. And so from the bottom to the top is L, and from the center to the top is L, but from the top to the bottom edge is 2L. Alright, so if you start with being told the thickness, the first thing you have to do is take that and divide it by 2, or you're going to not get the right answers, right? So you need to do that. Now the reason is it's like doing the radius on a cylinder or a sphere. Okay, so this L, think of it kind of like a radius almost. They talk about the initial temperature. The initial temperature is T sub I. Okay, I stands for initial. T infinity is the convection environment, and that's at 40 degrees C, and H is 150. And then they ask us really to solve two separate problems. The first one is fairly easy, the second one not so. Okay, so they're wanting to know when the center temperature is at 100 degrees C, and they're wanting to know when the face temperature is 100 degrees C. Now the center is designated by a subscript 0, so T naught is 100 for the center problem. And on the second one at the face, they're wanting to know when it's at the edge. Now remember, that's x equal to L. Okay, so the center is 0, the edge is L. So this is like saying T sub L, okay, would be one way to describe that. So let's do the first problem, the center one. I've actually kind of got this one already started over here, but we'll go through the numbers and then look at the graph. We're going to be doing this using the first of the charts of the Heisler charts. Remember, they're divided up, so you have plates, then cylinders, then spheres, and within each one of those you have a set of 4 graphs, but really it's 3. The second one is a blow up of this top region on the first graph, and I've got that shown over here. So this graph really is the same as this, it's just a subset of it so that you can read when it gets up scrunchy in this corner. And so the things I need to know is I need to know which of these lines I'm following, and that's described by this quantity 1 over the bio number, so that's K over HL. I also have temperature at the center compared to the initial, okay, along this axis, and at the bottom I have the Fourier number. Now when I'm looking for time, I'm really looking for the Fourier number because time is embedded in this quantity. So I'm going to be trying to find this using this procedure. So first of all, calculating 1 over the bio number, it's K over H over L. Okay, remember half the thickness. This is a dimensionless quantity, and I get a value of 11. And so I come over here and I see on the chart a line for 10, a line for 12. So eyeball where you think the 11 is, so I kind of split the difference, and that's the red line I've got drawn in. I also, if you have 3 things drawn on this graph, which is what we've got, then I need a second variable to be able to find the final third variable. So I also need this quantity over here. I'm looking for time, so I'm looking for the Fourier number. So this, I have all the information. The temperature at the center, that's my 100. T infinity is the 40. The initial temperature is 500. So let's calculate that. And so the temperature at the center minus T infinity, and divide that by the initial temperature minus, well, okay, that was not the right number. D13, okay, minus D14. Okay, so 0.13. And so 0.1, 0.2, because this is a logarithmic scale, I think that looks like about where 0.13 should lie. So that's the blue line, and you just go straight across. This one is choosing which of these curves I want, so the red, and they intersect right around there. Okay, go back to what we were doing there. They intersect right there, and okay, so let's go down to the bottom of this vertical line, and it looks like the value there for the Fourier number is about 23.5, maybe 6. Depends on how you read it, okay? Now the Fourier number is alpha t over L squared. So that means that t is going to be the Fourier number times L squared divided by alpha. Okay, so let's just calculate that. Okay, so the Fourier number times L squared divided by my alpha. Okay, and that gets me the time in seconds. Time in seconds is sort of silly units in this case because, you know, 760 seconds, I don't know how long that is. So convert that over to minutes. Remember, always try and get it into something that you think that just anyone would know what it meant. So about, 12.7 minutes. Okay, so that problem not too hard. You're only using one of these graphs, and that one should be something that you would be able to do fairly easily. Now the second problem is significantly more challenging simply because we have to combine two graphs. Okay, in this case I'm looking at for the time when when the edge is at 100 degrees. Okay, so this chart only tells me about the center and the initial. I'm wanting to know when the edge. Now logically, think about this for just a moment. Should this be a shorter time or a longer time than when the center got to 100? Okay. Now, for the edge to get to 100 when it's in a cool environment, I think that should have happened earlier, right? So at this point, the center temperature should be hotter still, and I'm expecting that this should be a shorter time. Okay. Now that's good information to think through because that way you have a way to do logic checks when you get down to your final answer. Make sure that you've got something that makes sense. Now to do this, since this chart isn't going to help us at this stage, I need something where I can relate the temperature at any point to this information. And so to do that, I need to go to the second chart, third chart, depends on how you count them, the one that looks like this. Okay. Now in this case, what I've got is I've got quantities of this 1 over the bio number down here, and I have various curves for x equal L, and then I have the temperature ratio for the temperature at any point divided by the temperature at the center. In this case, I know 1 over the bio number because that's the same value as I had before. Okay, so that's still going to be about 11, and if I insert a straight line there, well, let me pull this up so I can actually do that. Okay, so there's 10. 11 is probably about there. Again, it's a little further over than you probably think it is because of the fact that it's a logarithmic scale. But that's roughly where I need to go. And now which of these curves do I want? Well, x, when I'm at the edge, is L. Okay, x at the center is 0, then it counts up until I get to the edge, so that's L. So L over L is 1, so I'm looking along this very bottom curve here. So I'm going to see where this intersects. So these two intersect right here. Read straight across. Okay, and I get about 0.955. Okay, so that number there is going to be t minus t infinity over t naught minus t infinity. Okay. So I'll call that 0.955 is the way I read that. All right, so that's the theta over theta naught. Theta is the temperature at the face minus T infinity. So that was, temperature at the face was 100, T infinity was 40, so this should be a value of 60. Okay, now I can use this to solve for theta naught. Okay, agreed? Because this is just algebra at this point. So if this over this is this, then this over this is theta naught. Okay. And now I'm going to be going and taking this to the first chart. Okay. So if I'm going to take this to the first chart, I need to now take the theta naught that I just calculated and divide by theta initial, so I'm going to take that quantity and divide by the initial temperature minus T infinity. Okay, so I get 0.1367. Okay, the bio number doesn't change. It doesn't involve position, so that's not changing. I'm going to take this and I'm going to just simply raise this a little closer up here. It's about to there. Okay, notice that the intersection now has moved to the left. So I'll change my green line over for that. And it looks like I'm right at 23 for the Fourier number. Okay, so same formula as before. So this times my L squared divided by my alpha, which is way up there somewhere. Okay, 740 seconds, or if I take that and divide by 60, 12.3. So slightly shorter time. Okay, not a lot different, but it is less, and that was what we had as our expectation. Okay, so that is the first example. I'm going to do the second example in a separate video.